Hello students, I hope you will be okay. Thank you very much for your messages about the homework that I specified for you. But please students, please send me your homeworks by email. I think it is better because in WhatsApp I have many messages. I think about, let me to see it again. Yes, 50 messages about the homework that you sent for me, and it is it is really very difficult for me to check them message by message. It is very difficult for me. It is better, yes, I will give you my email. It is better to send you for me by email. This is my email, talibian@gmail.com. Thank you very much. Very good. Thank you very much. The only thing is that the subject of your email must be homework 1 from your name. Okay? Homework, for example, 1 from your name. For example, your name is, my name is Reza Talibian. I must write that homework 1 from Reza Talibian. Okay. And now we want to start our course. Let me share my screen for you. Okay, this is my screen, and let me to select the proper slide. Okay, I think we speak up to this, the delay modeling in VHDL, and now we must speak about the delay modeling in VHDL. Very good. The first thing is that I must sure that both voice and image are good. Is it okay? One of the students type for me, Mrs. Rasha, I have question. Please type your question. If you want to speak, no problem. The only thing is that you must raise your hand, and I will enable you. I will enable your microphone, and you can speak in the class. Okay. Now you can speak in the class, Mrs. Rasha. Mrs. Rasha, your voice is not in the class. Please enable your microphone. I think there is a problem. No microphone? Let me to enable you again. Yes. Now you can speak. Try to speak.
Salam, doctor. Can you hear
Salam.
me?
Salam.
Doctor. Can you hear me?
Yes, I can hear you.
Doctor, I asked about the multiplexer. architectures
About multiplexer, okay.
Architecture here, multiplexer. Some we write that number right effect. And we can
I have your voice with some misunderstanding. I can't understand you because your voice is some connections and disconnections. I can't hear you. I think it is better to type for me.
Okay.
Unfortunately, your voice is not clear. I can't hear your speaking. Excuse me. Multiplexer sometimes write unaffected, sometimes write other, in which case can I write one of them? Okay. Yes, as you can see, let me to show you in the slide. In some cases for multiplexers, I think in previous slide, yes. This is fifth, the number 5, the slide number 4. And this is the slide number 4. No problem. Yes, this is the multiplexer, and you can see that in some cases we write unaffected for the multiplexer. In some other cases we write others for multiplexer, and both of them can be correct. But which of them is better? It depends, really, it depends on the question. It depends on the problem that you want to solve. If you want to consider a latch at the output, in other cases, for example in high impedance and something else, you must select unaffected, because as I told you, unaffected means that we consider a latch at the output of the multiplexer. But if you don't want to consider a latch at the output, you must write others. Is it right? Is it clear for you? Okay. You're welcome. And now let me to speak about the new topic for you, about the delay modeling in VHDL. Delay modeling, it is important because, as I told you, in VHDL we expect that we can simulate, we expect that to simulate the time effects in VHDL and in digital circuits. Unaffected, the output want not 0 or 1 in other, yes, in other values For example, for select signal we have 0, 1, or for example, don't care, high impedance, we say others unaffected, for example. We write others unaffected, okay? Okay. For example, as I told you, we have F as the XOR of A and B. We know this, and we write this as a one line for VHDL modeling. But now we want to speak about the timing expressions or delays of the circuits. When we want to model the delays of the circuits, the only thing is that we add this expression after, and now we must write the timing expression. For example, 5 nanoseconds. And it is really the method of delay modeling in VHDL. What does it mean? What does it A XOR B after 5 nanoseconds? What does it mean? It means that we have an XOR circuit or an XOR gate like this, and the delay of this gate, it is F, the output of the gate, it is A, one of the inputs, and it is B, the other input, and the delay of this gate is 5 nanoseconds. The delay between input to output is 5 nanoseconds. Like this. Then if we have any event at the input, we can see this event at the output after, for example, 5 nanoseconds. For example, this event is in time 1, and this event must be in time 6. Do you understand up to now? Very good. If there is any problem or question, please type for me. Okay, no. What the W for that delay? What is the benefit of this delay? It helps us to have a real simulation, to have experience real situations. Because if we don't have any delay in digital circuits, it is not realistic, it is idealistic. But if we consider the delay of the gates, then we will have a real simulation, a real world simulation. For example, let me to give you some example like this. This is a full adder circuit. That is the delay for reaching input to output. For example, this is the full adder circuit. It consists of 2 XORs, 2 ANDs, and 1 OR gates. These gates have some delays. For example, XORs have 8 nanoseconds. 2 AND gates are 3 nanoseconds. 1 OR gate has 5 nanoseconds. If we write the delays of the circuits, we will see the waveforms but by delays. For example, if we simulate this circuit, this simple circuit, for example, we have like this. A, for example, A. Okay, this is A, signal A, and this is signal B. And about the time, yes, really, delay can be determined by us, or can be determined by our information about the system. For example, we know that this is some information that we can get from the, for example, the technology. We know that the delay of the OR gates is bigger than the AND gates. Then we can select, for example, as a symbol or as a simple 5 nanoseconds for OR gates, 3 nanoseconds for AND gates. Or for example, we know that the delay of XOR gates is, for example, a number between AND gates and OR gates. Then we can, for example, consider the delay of XOR gates as 4 nanoseconds. Okay, this is some general information about the digital systems. Or maybe the VLSI designer can give us specific information. For example, the VLSI designer give us, for example, the delay of the AND gate is specifically 2.7 nanoseconds. And for example, the delay of the OR gate is 3.1 nanoseconds. Then by this information, we can have a very careful simulations. It depends on our information. We have some information. Or maybe we have some information in general and we can determine the information. For example, we can consider all the delays of the blocks or circuits as, for example, 5 nanoseconds. This is our really condition or our really assumption. Okay, then to have a good simulation, it is better to assume some delays for the systems. To have a good delay, it depends for us. For example, to get some information from the VLSI technology, to get some information from some general information from the gates, or only to consider some delays as general delay for the gates. Is it clear? Do you understand? Okay, and now, very good. And now let me to come back to the example here. We consider an XOR gate here with 5 nanoseconds as delay, and we have some inputs A and B, and the inputs change, for example, in some special times. For example, here A is changed from 0 to 1 at 5 nanoseconds, and B is changed from 0 to 1 at, for example, 12 nanoseconds. And now we want to see the F waveform, the output, really the output waveform of the circuit. We know that the delay of the gate is 5 nanoseconds. Then for the output, if both of the inputs are 0, the output must be 0. And if both of the outputs are 1, both of the inputs are 1, the output will be 0. If only in this situation the one input is 1 and one other input is 0. In this situation, the output will be 1. And now we want to write the output waveform of the gate. Really, at the 0 time, the output is not 0 because the gate has delay. Then the first output is 5 nanoseconds later. Up to this, the output is X, undefined. Up to this. Or U, undefined. After this, the output will be 0. Why? Because the gate has delay. The delay of the gate is 5 nanoseconds. We can see the change of the input at the output after 5 nanoseconds. After 5 nanoseconds, it means that at time 10 nanoseconds, we can see the change at the output from 0 to 1. This is 10 nanoseconds. And this is 5 nanoseconds. Here in this point. Okay, very good. And when the output will be 0 again after 5 nanoseconds after B, 12 nanoseconds plus 5 will be 17 nanoseconds. Then after like this, and this. (17 nanoseconds). Okay, this will be, yes, in 5 nanoseconds, yes, F is 0. At 5, F start to be 0. At 10, start to be 1. At 17, start to be 0 again. Okay, do you understand this? All of you. And if there is any problem or question, please type for me to check it. Very good. And now we can come back to the slide and continue the example. S1 is XOR of A and B with delay of 8 nanoseconds after 8 nanoseconds. This is very simple. After time expression. Then we have final signal, assignment, the operation, and XOR, OR, etc. after time expression. Is it right? Then we can go to the next slide. Okay, now we want to speak some general things about the delay models in VHDL. Okay, up to now, is there any question? Okay. Okay, no problem. Very good. Now we want to speak about some general things about the delay models in VHDL. The delay models in VHDL specify for us the main delays that are used or that can be modeled or that can be written in VHDL. We have three main delay models in VHDLs. We call them, the first one, inertial model, like this. Inertial model. The second one, transport model or transport delay. And the last one, delta model or delta delay. Then we have three delay models in VHDL. As I told you. The first one is inertial model or inertial delay. The second one is transport delay or transport model. And the last one is delta model or delta delay. And now we want to speak and explain these delay models in VHDL. For the first step, we start by inertial delay model in VHDL. Inertial delay model in VHDL is really the delay of the digital gates, like this. As I told you, the delay is 5 nanoseconds. What does it mean? You see that this means that any change in input can be seen at the output after 5 nanoseconds. But we must consider some notifications about it. What are the notifications about it? If we have any change at the output, at the input, like this, but this change, if this change will be so little, it means that, for example, we have delay here. For example, in 5 nanoseconds, we have a change from 0 to 1. And we have another change from 1 to 0. For example, in 6 nanoseconds, it means that the period or the time of this change is only 1 nanosecond. The transistors or the basic elements of this gate must start and work, and the time that they need to work and make a good output is 5 nanoseconds. Then if the period time of changing at the input will be less than 5 nanoseconds, then we don't have enough time to have a good change at the output. Or we can say that we don't have anything at the output. Is it very important? Do you understand this? Let me to repeat it again. Yes, really, there is not any change at the output, or we can say that it won't be sent to the output. Let me write it again. For example, we have like this, something like this. And this. Here we have A, and here we have B. Not sensitive to little changes really, but if we have big changes with big time, it will be sensitive. It won't be sensitive to little changes. For example, here we have the time 6 nanoseconds, for example, here. And the next time is, for example, 8 nanoseconds. And now we want to speak about the output, here, F. As I told you, up to 5 nanoseconds we have undefined output, then up to this, for example. Up to this, the output is undefined. After this, the output will be 0. We expect that after 5 nanoseconds from 6, we will have 1 at the output, but the period or the time between changes is very, very little. It is only 2 nanoseconds. It is only 2 nanoseconds. And it is less than 5 nanoseconds. Then this change won't be transferred or won't be sent to the output. Then the output will remain at 0 all the time. In 11 nanoseconds, in, for example, here, in 11 nanoseconds, or in 13 nanoseconds, and etc. Because the time changes is less than 5 nanoseconds. This is the really the meaning of inertial delay of the gates. And all the gates, all logic gates, XOR, OR, and etc., all of them have inertial delay. Let me to come back to the slide here. As you can see, we have OR gate here. And this OR gate has one input to ground and the other input to input signal. If this input signal will be 1, the output must be 1. And if this input signal will be 0, the output must be 0. We consider two inertial delay model or two inertial delay time. The first one considering 8 nanoseconds as inertial delay. The second one considering 2 nanoseconds as inertial delay. If we consider 8 nanoseconds as inertial delay, this first change have 5 nanoseconds. This first change will be omit at the output, won't be seen at the output. Here you can see the only change is related to the second change because the period time of the second change is 10 nanoseconds and is bigger than 8 nanoseconds. Then we can see this change at the output after 8 nanoseconds. And we don't see or we won't see this change at the output because the delay is 8 nanoseconds and is bigger than 5 nanoseconds here. But if we consider 2 nanoseconds as inertial delay, we can see both of the changes at the output after 2 nanoseconds. For example, this change is at 5 nanoseconds. After 2 nanoseconds, we can see this change. And this change is at 15 nanoseconds. After 2 nanoseconds, we can see this change again. Okay, this is the meaning of inertial delay. Do you understand? Very good. Okay, very good. Then you can see that if we write, for example, F is A XOR or and etc. B after, for example, 5 nanoseconds, it means that the inertial delay of this gate is 5 nanoseconds. Is there any problem? Is there any question? Okay, very good. ES, what do you mean by ES? Who puts the value of the delay? As I told you, I explained about it. Maybe you have some information, some general information about the digital systems. Maybe you have some specific information, or you can get some specific information about the digital gates, or maybe you consider something. This is only some general consideration. Okay? Yes, it is variable and it depends on you and your information. Very good. Another question? Okay. And now we can go to the next delay, transport delay. What does it mean, transport delay? It is specifically returns to the delay of data lines, data transferring buses. For example, clock, data bus, and etc. Something like them. Yes, bus system. Specifically bus systems and bus lines. For example, you have a line for clock. You will have a delay. If you have any change at the input, you will have this change at the output, but with a specific delay. And you don't have any inertial delay in bus systems or in bus lines, because you don't have any transistors, any elements, basic elements. You only have a wire. Then everything will be happened here must be seen at the output after a delay. This is the delay line. This is the delay of the gate of the, for example, the clock, the bus, or it's something like this. Then this delay is different from inertial delay. For example, you consider here as A point, start point as A and final point as F. You must write F is A, but you know that there is a delay here. If you write after, for example, 50 nanoseconds, this after means inertial delay. But you know that this delay is not inertial delay. This is a transport delay. And this is our question. How can we model this new delay, this transport delay? And now we want to speak about it. The only or the main method is that we add this keyword, transport, at the start of the line. F is A, but F is transport of A after 50 nanoseconds. What does it mean? It means that F is A after 50 nanoseconds, and this delay is a transport delay. Then if we have any change here, the output will be the same, but with a shift in time. This time shift is 50 nanoseconds. And this is not important that the change is less than 50 nanoseconds or bigger than nanoseconds, because we must write all of them with only this time shift. Do you understand? The only two persons understand. 3, 4. Only type a plus to tangible in all cases. What do you mean tangible in all cases? The last line, this line. We want to model the transport delay. The transport delay, you have two steps for better understanding. The first step is that to understand the meaning of transport delay. The meaning of transport delay is that the output will be the input after a time shift. And it is not like inertial delay. Every change in input must be at the output with a special delay time. Yes, it is not like inertial delay. And the second step is that how can we write this special delay in VHDL? For example, we want to say that f is a with some special delay. The only thing is that we must add this keyword transport at the input of expression. For example, we write f is transport a after 50 nanoseconds. Step 1 and step 2. Do you understand? This is a keyword that is reserved transport that is reserved in VHDL. You're welcome. Any other question? Mr. Yasser Abdul Karim, do you understand? How do you write if we have two delays in VHDL? Okay, this is a good question. And I will tell you in the next slide. But before this, I must emphasize to this point that really in digital gates the main delay is inertial delay, and in digital buses the main delay is transport delay. In some special cases we can use from both of delays, both inertial and transport. How? I will explain for you. Up to this, is there any problem, question? Okay. Okay. Okay, let me to come back to the slide. This is the example from transport delay 1 nanosecond, input, output, time shift in 1 nanosecond. And this is the reply to Mr. Abdul Karim question. We want to use from both of the delay types. Okay. Let me excuse me, only wait for 5 minutes. I must speak to one of the students here, and I come back to the room, to the class, and continue. Only 5 minutes. Now, let me to continue our speaking about the delay model. As I told you, this is a special example. Let me to come back to this previous example. Okay, this example means that we have two time expressions. The first one is 2 nanoseconds and the second one is 5 nanoseconds. As you can see, S, we must write this S. S is reject 2 nanoseconds inertial. A, X or B after 5 nanoseconds. It means that we have two time expressions. Let me write for you. Then we have two time expressions. For example, T1 and T2. The first one is 2 nanoseconds. The second one is 5 nanoseconds. But for 2 nanoseconds, it writes reject. Reject 2 nanoseconds inertial. It means that we have an inertial time expression with the amount of 2 nanoseconds. But the second time expression is for output, really waveform. It's for output showing. It means that every change at the output must be shown after this time expression. After this time expression. Then you have two time expressions. The first one is reject time or inertial time. The second one is really like transport delay. You don't have my voice? Okay. Then now for example, we want to write the inputs and output waveform. For example, for A and B. We start by A. It is at first, for example, 0, 1, 0, then 1, Mr. Ahmad Sarkar, approve you if you want to enter the room. And then this will be 0, remain 0, change to 1, remain 1, change to 0, and then remain 0, change to 1, and remain 1. The other input is B, and it is 0 in all times. B. And now we want to write F. Let me to specify for you the timing of A. The timing of A. Okay, this can be a start from 10 nanoseconds. The next one is 11 nanoseconds. The other one is 14 nanoseconds. The next one is 17 nanoseconds. And the last one is 23 nanoseconds. Now we want to write, and as I told you, before 2 nanoseconds we don't have any output. Why 2? Because 2 nanoseconds is inertial delay. But every change must be seen after 5 nanoseconds. Then up to 5 nanoseconds we don't have any output. It will be undefined. Undefined. Up to 5 nanoseconds I will write. After this it will be 0. Okay, the first question. The timing of this change is 1 nanoseconds, 10 to 11. This change can be seen at the output or not. Yes, because the time of this change is 1 and it is less than 2 nanoseconds, and it won't be at the output. Thus then we can pass through this. But the next change can be seen at the output because the time is from 14 to 17. The time of the change is 3 nanoseconds and it is bigger than 2 nanoseconds. Then it can be seen at the output after 5 nanoseconds, like this. Change to 1. And then the other change to 0 after 5 nanoseconds. Be 0, and then other change to 1 after 5 nanoseconds. Okay, let me to write the time expressions. for the output 14 plus 5 will be 19 nanoseconds. The other one 17 plus 5 will be 22 nanoseconds. And the last one, yes, 28 nanoseconds. Inertial time is only 2 nanoseconds. 5 nanoseconds is a time shift between input and output. Okay, is it right? Do you understand? 28 because 23 here plus 5, and this will be 28. If we don't have any other change, it considers this unlimited. Then this will be bigger than 2 nanoseconds as reject time. Reject as an inertial or reject time. Both of them are correct. Okay, very good. Is there any other question? Okay. The last thing that I want to speak about is about the delta delay model. The delta delay model is not in physical, is not in real world. The only thing is that it is a technique that we use this in the VHDL editor. And what about the delay model, delta delay model? We use this delta delay model in the VHDL codes that they don't have any delay, like this. These lines don't have any delay. But we know that, for example, if we have any change in input 1, for example here, input 1, we will have a change in S1. And if we have any change in S1, we will have other change in S3. Then we can see that we have something like order. Input 1, second, S1, third, S3, fourth, Z, or output. How can we consider this order? Because we speak for you that VHDL is a concurrent environment. But we know that here we have order because of the order of the gates. Input 1, S1, S3, Z. In this situation, VHDL writes something like this. VHDL writes like this. For example, S1, let me change it to black. S1 is not in 1 after delta. Delta is a time step. It's not important. All the lines will be changed like this. S1 is not in 1 after delta, after delta, after delta, after delta, after delta. Then we can see like this. For example, input 2 have a change here. After delta, S2 have another change. At the same time, S3 have another change after delta. And Z output will have another change after delta or 2 delta. After all, we have a limit. We send delta to 0. Then delta will be 0. 2 delta will be 0. All of them will be 0 at the same time. Then this is a special technique only for VHDL editor. It is not important for you. The important thing for you is that you must consider the concurrent working of VHDL lines. Is it right? Why we do the 0 state? It is example, no 0 state, no 1 state. This figure, this waveform is example. The only thing is okay. We send, for example, in limitation, in arithmetic, in algebra, we say, for example, we write like this. For example, we say x will be sent to 0, for example. We really send delta to 0. Then all the parameters will go to 0 and we will have concurrency. Do you understand? The other students? Only 4 students? 3 students really. Mrs. Zainab, Haba, Rasha, Zuha, Marve, and Yasser, Mr. Yasser, Ahmad. Okay, very good. Is there any special problem or difficulty about it? Okay, very good. And the last slide is that we want to generate a waveform. How can we write it? We must write f is 0, difficult. No problem. If you understand, it is no problem. Difficulty is not important thing. If you don't understand, easy things are difficult. Okay? Do you understand this? Mr. Ahmad Muhammad. Yes, okay, very good. Then this will be easy because you understand it. The last one is about waveform generation. As you can see, f is 0 and 1 after 10 nanoseconds. 0 after 25 nanoseconds. 1 after 30 nanoseconds. And we write the waveform. You can see that after. All of them are from 0. After 10, it means that we have a change at 10 nanoseconds. After 25 nanoseconds, it means that from 0, we have change at time 25 nanoseconds. Then the period of change between one change to the second change is 50 nanoseconds. The only thing is that. Then after, when we use after, it means after from 0. Do you understand this? Okay. Then this slide is ended. If you have any question, please type it. If not, I can end the class. You're welcome. Thank you very much from you. Very good. Then I hope you will be okay and good times at the remains of the day. Remain times of the day. خسته نباشید. Thank you very much and goodbye. Thank you very much. خدا حافظ.